Hi, so far in chapter 10 you have learned about the gravitational field related ideas including gravitational force, gravitational potential energy, etc. And so now we are moving on and transit to the electrical field. And the reason why we covered that way, instead of teaching 10.1 and 10.2 like in order, we go for the gravitational first, because if you understand those things, then you can borrow the idea and you can understand the electrical much more easily and faster. And so have a look of the data booklet here. If you look at this, especially the table here, this is the most important table that you should find. You should find out they are basically symmetrical, and that is actually the beauty of the universe itself. We find the forces are actually quite similar. So if you really try to compare them in more specifically, you'll find out in gravitational point of view, we would concern about the mass, while for electrical, the mass will kind of become charge right here. And so in that case, you will find, for example, the first equation you learned, which is this one, gravitational law, F equals to g/mm over r squared. You'll find very similarly, you just have to change the mass to the two charge of the two objects. And of course, the constant would not be the same, changing from universal constant, gravitational constant to the Coulomb constant, which is again is found from the experimental approach, and this is just a number, all right, in the equation. But then the relationship is very similar, and therefore the characteristic would also be very similar. You should also find here that is the potential energy of gravitation and also electrical is again exactly the same, except for gravitation there's negative here, while for electrical it actually depends on the charge. So cause for electrical, the only thing that is a bit different is for electrical you have positive and negative. For gravitation, strangely, scientists only find the usual gravity, right, which is an attraction force towards each massive object. We don't, so far at least, we don't actually find anti-gravity which repel you because of those mass. Great. So this is something that kind of stick in the scientist's mind for a very long time, and we still don't understand that. So of course, if you can somehow find out or even create anti-gravity, for sure that you get Nobel Prize. NANI? Okay, moving on. Here we can see that this is the gravitational field strength. Okay, and you can do it by dividing the gradient, finding the gradient of the V against R, the potential against the distance, and you can find the gradient. This is something that we mentioned in an earlier video. If you don't remember, you can go back and check it out. So for that graph, if you look at the gradient, that means the slope of whatever it is, then it will tell you the gravitational field strength. So that will be the same for electrical. You have to look at the electrical potential, and if you divide it by the distance, of course now we are talking about the tangential slope, and so that would tell you the electrical field strength. Okay, so again these are very similar, and not to mention for gravitational potential and electrical potential, again you can see the constant will change, and then the mass will change to the charge, and the rest will all be the same. Okay, so let's also take a look at the list provided by the IBO officially. So I will want you to go through the list by yourself from 10.1 understanding all the way, including the guidance as well, to 10.2 until the end. Go and check out which of those are learned already in gravitation, and whatever the rest should be the electrical. So pause the video and try to put a tick next to the one that you learned.
A few moments later.
Okay, let me also go through it as well. Gravitational field, we have done it, and again we can borrow the idea and understand electric field. we have learned gravitational potential already, and we can borrow that to electrical potential. Next one is called the field lines. I think this is referring to the general idea of what field lines is representing. For example, what does it mean by a more dense field line? And that should be related to the field strength, right, of that particular force, so gravitational force or electrical force. Equal potential surfaces will be the line that joins the positions where they are of the same potential. So again, this can be applied to gravitational or electrical. So in fact, you have learned it from gravitational already. Next, representing sources of mass and charges, line of electric and gravitational force, field pattern using appropriate symbolism. I think this is already done. So how you can use those arrows representing the field, knowing that they cannot cross each other, the symbol, yeah, etc. So I think that shouldn't be anything difficult. Mapping fields using potential. So again, this should apply to both gravitation and electrical. And the idea that you should have is for the equal potential line. For example, if this is I don't know, 0V, 2V, and then 4V, and then it should go with a field line that is joining them in right angle. Okay, sorry I didn't draw very well, but then later on we have more example, and again I suppose you have learned it already. And it should go from high to low, I think, is it? Let me double check. If we have a plate of electric field, it should go from positive to negative. And if you have, yeah, this is high, this is low, right? And so yeah, so high to low, so it should go like this direction from 4V to 0V. Oh, and in fact the next one describing the connection between equal potential surfaces and field lines is just exactly what I said about the 90-degree, all right, geometry relationship. Next, electrostatic fields are restricted to radial fields around a point or spherical charges. So it could be a positive charge and it should radiate out, positive to negative, yeah, so it should radiate out. Or spherical. Spherical is just a one with bigger. And then another idea that you don't really officially learn, but then inside the sphere, metal sphere, for example, the potential is going to be 0. So when you draw the field line, you only have to draw those field lines outside of the sphere. Alright, if this is positively charged. The field between 2-point charge and uniform field between parallel plates. So parallel plate, like basically like what I drew here, of course more precisely, it should be of a uniform density, and at the side there will be something called the edge effect, which you could also draw, so it will be more curved, and obviously that would lower the density of the field line, and that means it will be slightly weaker comparing to the region at the middle. And I have to admit, for the 2-point charges, because for electrical is a bit different from gravitational, where gravitational, like I said, is always attracting. So if you have moon and earth, both are attracting the other objects. But for positive charge and negative charge, when you put them together, and if you put a test charge, no matter the test charge is positive or negative, one of the force experienced with repulsion, one of them will be attraction. So the field line would look slightly different, right, from the gravitational one. So later on, there's actually an activity that you can do and try it out in a simulation. Next, gravitational field, blah blah blah. Yeah, of course we have done it. Students should recognize that no work is done in moving charge or mass in an equal potential surface. So yeah, I mean that's the whole idea of why it's so important. Within the line that is joining the same potential, since there's no potential change and therefore no work needs to be done in theory. Of course, this is talking about there's no kinetic energy increasing, and so since potential there's no increase or decrease in potential, and therefore you don't have to give extra energy. Okay, 10.2, potential and potential energy, just like the equation that we have just mentioned, it should be quite direct and straightforward to you. Potential gradient is basically what I mentioned about the field strength. Potential difference, just delta V basically. Alright, same idea in gravitation, bringing to the electrical. Escape speed is something that we only have in gravitation, at least for this chapter. So it's not easy to talk about for electrical, like it escaped from that. So it's mainly referring to the gravitational. Orbital motion, orbital speed, and orbital energy, again, is referring to gravitational also, which you have done it. Forces and inverse square law behavior. So this was actually shown by the equation because the force was gmm over r squared. So this is the inverse square law behavior, same as the electrical force, which is k q1 q2 over r squared. So you also have r squared at the bottom, so inverse square law behavior. Next, determining the potential energy of a point mass and potential energy of a point charge. So yeah, basically these are the things that you have learned, and the equation actually you have learned is applicable to point mass and point charge only. Point is the word that you look for. Okay, and so that means if you have a kind of irregular shape which carry charges, then it wouldn't be as that easy to just apply that equation to it. Solving problem involving potential energy, yes. Next, determining the potential inside a charge sphere. So like we said, inside a charge sphere, okay, just now I mentioned it wrongly, but I hope you have seen the notification, that inside the sphere, the force is going to be zero. There's no force. The other idea you can bring from gravitation is, I'm not sure if you have heard about what if the Earth is a shell, like eggshell, right? Very thin shell of layer, and inside is basically empty, okay? Or you can fill it with air equally if you like to. And so in that case, if you are inside this Earth gigantic shell, what kind of gravitational force you will experience? The answer is that the force would equal to zero. Okay, and the reason is that in a qualitative approach is that you can imagine the force is going to spread out in all directions, and depending on how much portion that you have. So for example, you may think that, oh, then because you're kind of closer to the right hand side right here, right? But then if you think about for the left hand side, you have more mass, although they are further apart, right, from you. So in total, they kind of cancel each other at the end, and therefore they will be able to be equal in magnitude. And so no matter where you are, even if you are sticking your face to the shell, you will still have the force. Because for example on this side, then the force that pulling you to this side, they are far away, but then you got many more mass comparing to the one on the left hand side here. They are closer, but then the portion will be much less. So interestingly and mathematically, we can find out no matter where you are within this shell, the force is going to be zero. And that is the same idea for a charged sphere, because you have, for example, the charge evenly distributed outside of the sphere. And so if you have a point charge inside, no matter where you are, the electrical force is still be the same. If you are interested, go and check out Gauss' law. So Gauss, which is a very famous mathematician actually. So you can actually try to prove this in a quantitative analysis. So yeah, check it out. So again, so the takeaway is the force would equal to zero, but that it doesn't mean the potential will be zero, because when we try to recall those equations, force is going to be proportional to gravitational field strength or electrical field strength. And so G at the same time would equal to delta V over delta R. So it's the change of potential. So if force is 0, that actually means that the change is 0 only, not the value. Just like if you have acceleration, acceleration is 0, doesn't mean velocity is 0. Velocity could be a constant number, while acceleration is being 0. So here we will have the V potential to be a constant. Okay, and that constant value is the same as the number, the magnitude, as if, for example, this charged sphere is a point mass. And therefore, later on you will find on your textbook, you will find a diagram like this. Okay, and this is within the sphere, so you have a constant potential. And once you are away from the surface of the metal sphere, then you will start to drop with a relationship of 1 over r, because that's the equation itself. So this is something that you can think about, and if you try to differentiate this v with respect to r, that means you are trying to find out the gradient simply, then you'll be able to obtain the field strength graph as well. So obviously here is a horizontal line, so like I said, the force is going to be 0. Okay, next few things I believe is involving gravitation, so we have done it. And this is also, or actually no, charged particle. So the idea is also the same. You probably will be using the force equation, Coulomb force, F equals to K Q over R square, and also the circular motion equation, because that could be the force that maintain the motion of the charged particles. So that is something we will talk about. Lastly, solving problem involving forces on charges and mass in radial and uniform fields. So that could be related to having a parallel plate, and there will be an electric field, and maybe talking about an electron that are moving inside this field and how that would change the direction, etc. So it will be again something that we will cover later on. Okay, guidance. So it said the orbital motion is considered only the circular orbit only. So don't worry about other things like hyperbolic, parabolic orbits. Alright, those would not be included in IB physics. Otherwise, it would so much more complicated. Next, both uniform and radial fields need to be considered. Yes, of course. Students should recognize that lines of forces can be two-dimensional representation of the three-dimensional fields. So this is saying that even though when we try to draw the field lines on a piece of paper, it is two-dimension, but of course in reality it's three-dimension. You can go and check out the 3D magnetic field lines. People can just simply illustrate by putting a magnet inside a box of iron filling, and you can see those iron filling will form a 3D shape of magnetic field line simply. And lastly, here is that you should assume the electric field everywhere between the parallel plates is uniform, except when you have the edge effect at the very boundary of the plate. So allow me to draw again. So if I have a positive terminal connected to a negative terminal here, then the field line should be drawn in the same uniform density, probably something like this, okay, with the side showing a curve, which is the so-called edge effect. And the most important idea is within the middle region, like the core region in the middle, since the field line density is proportional to the field strength, and field strength is proportional to the force. So that means if you have a charged object, for example an electron, if it is here, if it is here, if it is here, the force is going to be the same in magnitude and also direction. When I was a student, I was very confused with this because intuitively, when you try to, I guess, just think directly, you may think that, oh, if this is negative, then it should get a stronger force when you're at the two sides, right? When you get closer to positive plate or negative plate, the force should be bigger compared to the one in the middle. However, it's going to be the same. So this could be seen by looking at the density of the field line. So it's the force is actually the same everywhere within this region between the parallel plate. Okay, so that is all for this video, which should help you to transit from the gravitational related idea to the electrical later on. In the coming few parts of video, we'll try to do different practice and exercise, and I'll see you again in the next video. Bye.